So peptide bonds are very important. If it wasn't for peptide bonds, then the amino acids could not hook up together. And if they can't hook up to make these polypeptides, then we cannot form proteins. And proteins, of course, as we said before, is a major workhorse in your body. So peptide bonds is the glue that, or are the glue that holds the basic amino acids together to make these globular proteins or fibrous proteins or whatever the case is that your body decides to use. However, there's also another important bond that we need to talk about other than a peptide bond, and that's this thing called a sulfide bond. And a sulfide bond is very important. I call them sulfide bonds. However, in the text, and you'll also hear people be a little bit more proper, and they will say disulfide bonds. So a disulfide bond and a sulfide bond, I'm going to regard as the same thing. The proper term, though, is disulfide. There's really only one amino acid that undergoes a disulfide bond. And these things are very important, again, because bonds give stability, and stability makes molecules happy. And we want our molecules happy, and we want our molecules stable because we don't want our proteins to just spontaneously break down for no reason, right? Okay, so if I take a look at cysteine, cysteine is a structure that we have already talked about. I told you that it was very important and for you to memorize that structure. So let's see if we can draw cysteine from memory. So C double bond OO, and then we've got this alpha carbon, and then we've got this NH3 group. And then off of this alpha carbon, we have the cysteine R side chain. And this side chain for cysteine is a CH2SH. Okay, so there's cysteine. And one molecule of cysteine can actually come into the same space of another molecule of cysteine. And these two cysteines could maybe hook up together and say, hey, you want to go out for a while? And the other cysteine says, yeah, sure, why not? So I'm going to take this SHCH2 and I'm just going to draw this amino acid kind of upside down. So I'm only doing this because it's going to be easier to show on the sheet of paper if this is how we draw it. So one molecule of cysteine comes into the other molecule of cysteine. So I get 2 moles of cysteine that come through. Oxidation happens here. Okay, so oxidation. And when this mild oxidation takes place, what we see is that the hydrogen from this one disappears. The hydrogen from this one disappears. And we see a brand new bond that forms between the 2 sulfurs. And that, ladies and gentlemen, is what we call a disulfide bond. Well, that kind of makes sense, right? A disulfide bond. Okay, well, I don't really like the way that that is drawn. I probably would want my sulfur and my CH2 together a little bit closer, so that way we can really fully see that these 2 molecules are now joined together by this new disulfide bond. So disulfide bond, 2 sulfurs involved in the bond, and there we go. It's another type of glue that can hold these amino acids together. And disulfide bonds are also called disulfide bridges. And here I'm spelling everything wrong. They're also called disulfide bridges. And disulfide bridges are the only covalent bond that's found between non-adjacent amino acids in peptides and proteins. So the purpose of the disulfide bridges or the disulfide bonds is that they really tend to give us a better overall shape of a protein. And they link different parts of the protein together with each other. So for instance, let's say that we've got this kind of long floppy amino acid chain. And this amino acid chain has a N terminus, right? So we're using some terminology that we have, and it also has a C terminus, so a beginning and an end. What happens is that maybe somewhere along this chain we have a cysteine, and that is a S carrier, a sulfur carrier. And let's say that over here on this side we have another cysteine, and that's another sulfur carrier. So these two cysteines basically come together and make this disulfide bridge. And you can kind of see why we call it a bridge now, because it kind of bridges one part of the molecule to the other part without going completely around the actual protein itself. Imagine this as Greenfield Lake, right? So I don't want to walk the entire 5-mile span around Greenfield Lake. What I want to do is that I want to walk a little bit of it, and then I want to take a shortcut and go across the bridge and hook up on the other side, and then finish on around. So that's the disulfide bridge. It really just hooks up different parts of the protein, and there could be a number of these. So it doesn't have to be one. There could be 14, there could be 400 different disulfide bridges in a protein. It just really depends on how big the protein is and how many cysteines that we have in the actual structure itself. So these things are cross-linkers, and they hook up one part of the protein to the next, and this is what we call a disulfide bridge or a disulfide bond. So that's the purpose of them. That's why they're there. Something that we need to talk about in the laboratory is how could I basically get this oxidation to happen. There's two things that you could use. You could use Br2 or I2, and both of these help form the disulfide bonds that begin to happen between these two amino acids. Your body, of course, doesn't really use bromine or iodine. It uses different enzymes and things because it's not really a true laboratory like you work in, right? So it has to have access to a couple of different things than what you do not have. So if we were doing it in a lab, we could have this accomplished by choosing bromine or iodine to go in and create these disulfide bonds or bridges for us. Okay, so again, more glue that holds the protein together. If you take a look at insulin, you know, insulin is a protein. Insulin's very important, and if it controls really the glucose levels. So this goes back to kind of the carbohydrates. If you take a look at insulin, insulin is a polypeptide. And this polypeptide is very important, and there's two strands of the protein. So if you take a look at insulin, typically what we draw is just kind of a straight chain up here at the top and a straight chain down here at the bottom. And we call this the A chain and the B chain. And we know the proteins that are, or the amino acids that are in this protein. You can actually look that up. You can go in, you can look at the amino acid order that makes this protein for A chain and B chain. And what you'll find out is that these two chains are held together by disulfide bridges. And there's probably two of them, I believe. One, let's say, in the beginning, and one, let's say, down here at closer to the end. But these disulfide bonds basically hold insulin together. So if you destroy these disulfide bridges, these two chains separate from each other and insulin is no more, and you can't really process glucose properly if, of course, you do not have the insulin that will actually do it for you. So not only that, but we also see disulfide bonds in curly hair. So the curlier your hair is, the more disulfide bonds that you have. Very early on, you know, back in the day, permanence used to be, you know, the greatest thing ever. So you would see women go in, I don't want to be sexist, but probably men as well. You go into the hair quarters or salon, and you sit down and you get your hair rolled in these tight little curlers, and then they bring out something that smells like rotten eggs, and they squirt it all over your head, and you sit there for 30 minutes, 45 minutes while it processes, and then they kind of wash it out and rinse it. Well, the reason that it smelled like dirty eggs or rotten eggs is because that's the typical odor that we associate with sulfur. So if you've got water problems and you have high sulfur content, you're smelling the sulfur compounds that are coming from that water. So the very same thing is happening with permanents. These are sulfur containing compounds, and what's happening is that they roll your hair into a tight roll, and they put this compound that smells like rotten eggs on your hair, and then your hair will take the cysteines that are making that protein up, because hair's protein. It will take the protein of your hair and basically hook the sulfurs up together and make these disulfide bonds. So when they take the roller out, your hair is already kind of locked into place with this tight curl, and the tight curl is coming from your cysteines that happen while you're sitting in that chair. We do have a new term that we use to describe the two cysteines when they hook up. So two cysteines, cysteine. I'm saying that very carefully, cysteine, because when two cysteines hook up and they give me this disulfide bridge, we call this cysteine. So there's a slight difference in how you pronounce them, cysteine and cysteine. So the disulfide bond makes a cysteine, and cysteine are two cysteines that are hooked up together. I know it's a tongue twister. You'll figure it out though. So there's kind of the disulfide bonds and really how they relate to our everyday life. Curly hair, you've got disulfide bonds. And then insulin, your glucose transporter and helper, well, this is due to disulfide bonds. It's holding your insulin together, your insulin protein at least. So there's a story with disulfide bonds, just another piece of glue that begins to hold these proteins together. Take a look, read the section in your book about diabetes and straight or curly hair. It will go into detail about the disulfide bonds and why it's important, and it will also tell you a little bit about diabetes as well. So it will have the insulin receptor on there, it will show you the insulin primary structure on there, it will show you the amino acids that are involved in the insulin. It's a very well-known protein because it's very simple and it's very short and sweet, so we can isolate insulin very well. We can break it up, we can look at the proteins and how they've ordered themselves, and the bigger proteins, well, the more complicated that analysis is going to be. But insulin is very nice for us because it is short, simple, and sweet. So in the next video, we'll go through and we'll take a look more on the protein chemistry and how these things begin to hook up and what happens in them after they do hook up to make these to make the glue that begins to hold these proteins together.